There's a number that keeps showing up in astronomy papers over the last 2 years, and almost nobody outside the field has noticed it. That number is 13.4 billion. It is not a distance in kilometers. It is an age. The age of the universe in years, at the exact moment a beam of light left its source and began the longest journey any object has ever made toward planet Earth. That light finally arrived. A telescope caught it, split it into a spectrum, and handed astronomers a problem they still have not solved. Because the thing that light came from should not have been ready yet. Not even close. By the end of this video, you will understand why some of the most careful scientists on the planet are quietly saying the same uncomfortable sentence to each other. The early universe grew up too fast, and we do not fully know why. Let's start with something almost nobody thinks about, which is that when you look up at the night sky, you're never looking at now. You're looking at the past. Light is fast, but the universe is bigger than fast can fully solve. Sunlight takes about 8 minutes to reach us, so the sun you see is 8 minutes old. The nearest star beyond our own takes over 4 years. And once you start looking at galaxies instead of individual stars, the numbers stop being minutes or years and start being billions. Some of the light hitting our telescopes tonight left its source before Earth even existed. That is not a metaphor. That is literally how old the information is. This is exactly why the James Webb Space Telescope was built the way it was. Webb does not primarily look at visible light, the kind our eyes can detect. It is tuned to infrared, and there is a very specific reason for that. As the universe expands, the space between us and any distant object stretches too, and it drags the light traveling through that space along with it, stretching its wavelength in the process. Astronomers call this redshift. The further back in time you look, the more violently that light gets stretched, sliding out of the visible spectrum entirely and landing deep in the infrared. So if you want to see the very oldest light in existence, you cannot use a telescope built for visible light. You need something built specifically to catch light that has been stretched almost beyond recognition. That is Webb's entire reason for existing. Now rewind the clock all the way back, past every galaxy, past every star, to the first few 100 million years after the Big Bang. Astronomers have a name for this period, and it is a good one, the cosmic dark ages. Not dark in the poetic sense, dark in the literal physical sense. The universe at that point was filled with a thin fog of neutral hydrogen and helium gas, and that fog was opaque. Light could not travel freely through it. If you had somehow existed there with a working pair of eyes, you would have seen nothing at all, in every direction, for hundreds of millions of years. What ended the Dark Ages was gravity doing the only thing gravity knows how to do. Slightly denser pockets of gas pulled in more material than their surroundings. That extra material meant extra gravity, which pulled in even more material, and eventually, in certain pockets, enough matter piled up in one place to ignite nuclear fusion. The first stars turned on. These were not modest, well-behaved stars like our sun. Best estimates suggest they were monstrous, hundreds of times more massive, burning through their fuel violently and quickly, blasting out enormous amounts of ultraviolet radiation. That radiation ripped electrons off the surrounding hydrogen atoms, carving clear bubbles through the cosmic fog. Those bubbles expanded, merged with neighboring bubbles, and eventually the fog cleared completely. Scientists call this process reionization. And the point where it really gets going is often called cosmic dawn. Every telescope pointed deep into space is, in some sense, trying to catch that exact sunrise. For a long time, models of cosmic dawn made a fairly reasonable prediction. Galaxies from this era should look small, faint, disorganized, and chemically primitive. Barely there smudges of young stars still figuring out how to become a real galaxy. That prediction held up reasonably well right up until Webb actually started looking. Here's where things get strange. Since Webb became fully operational in 2022, astronomers scanning its deepest images have kept finding candidate galaxies from this earliest era of cosmic history, and a surprising number of them do not look faint or disorganized at all. They look bright, structured. In some cases, suspiciously mature, as if they had been building themselves for far longer than the timeline allows. At first, each one of these was treated as a curious outlier, a strange exception worth a follow-up look, but outliers are supposed to be rare. And this stopped being rare. To understand why that matters, you have to understand how astronomers confirm these discoveries in the first place, because a photograph alone is not proof. A bright dot far away, imaged in only a few infrared filters, gives you a candidate, not a confirmed answer. Real confirmation requires spectroscopy, passing the object's light through an instrument that splits it into its individual wavelengths. The same basic principle as a prism splitting sunlight into a rainbow, just built with extraordinary precision. Certain elements absorb and emit light at very specific, well-known wavelengths. When astronomers see those exact fingerprints show up in a spectrum, stretched by a precisely measurable amount, they can calculate redshift directly instead of just estimating it from color and brightness. That number becomes the object's cosmic timestamp, telling you almost exactly how long its light has been traveling, and therefore how far back in the universe's history you are actually looking. When teams started running these spectroscopic follow-ups on the most promising early candidates, a pattern emerged that nobody was fully expecting. Galaxy after galaxy, once confirmed, turned out to be too luminous for its size and age. Some were compact enough to fit inside what we would normally call a dense star cluster, rather than a full galaxy, yet were producing enough light to rival galaxies many times their size, operating billions of years later. Pound for pound, they were shining far more intensely than current models of early star formation would predict. There is a second layer to this puzzle that is arguably even stranger than the brightness problem, and it involves chemistry. In the earliest moments after the Big Bang, the universe contained almost nothing but hydrogen, a smaller amount of helium, and a barely there trace of lithium. That's it. Every heavier element that exists anywhere, the carbon in your body, the nitrogen in your DNA, the oxygen you just breathed in, had to be forged inside the nuclear furnace of a star and then scattered back into space when that star eventually died, usually in a supernova. Only after that scattered material gets pulled into a new generation of stars, and those stars live and die in turn, does a galaxy's surrounding gas start accumulating a genuinely rich chemical mixture. This is not a fast process. It takes multiple full stellar generations, each one living for millions of years and dying before the next one can begin. When astronomers examined the detailed spectra of several of these ultra-early confirmed galaxies, they found chemical signatures that simply should not have had time to form yet. In more than one case, the ratio of nitrogen to carbon in the surrounding gas came back unusually, almost impossibly high, for an object barely a few 100 million years removed from the Big Bang. That specific chemical signature is not unfamiliar to astronomers, either. It closely resembles the pattern seen inside globular clusters, dense, ancient collections of hundreds of thousands of stars that orbit around the edges of galaxies like our own Milky Way, long treated as some of the oldest structures in the observable universe. Finding that same fingerprint already present at the very dawn of galaxy formation suggests that whatever builds structures like globular clusters may have started working almost immediately once the cosmic fog cleared, rather than gradually over billions of years as previously assumed. So what could actually explain all of this? Astronomers researching this puzzle have put forward a handful of serious possibilities, and it's worth walking through them honestly, because each one comes with real consequences for how we understand the universe's early history. The first possibility is that star formation in the extremely early universe was simply far more efficient than current models assume. Instead of gas slowly and messily collapsing into stars over long stretches of time, with a lot of material never quite making it, early gas clouds may have converted into stars unusually quickly and with unusually little waste. If that's true, it would mean galaxies could genuinely build up mass and light output much faster than textbooks currently describe. The second possibility involves the very first generation of stars themselves, sometimes referred to by the technical shorthand population 3 stars. These would have formed directly out of pure, unenriched primordial gas, with none of the heavier elements that normally help regulate how stars form and how large they can grow. Without that regulation, some models predict these first stars could have been extraordinarily massive and extraordinarily hot, burning bright enough that a comparatively small number of them could genuinely outshine an entire modern galaxy's worth of ordinary stars. If a young galaxy happened to be dominated by a batch of stars like that, its extreme brightness would start to make a lot more sense. The third possibility is more dramatic still. An early, actively feeding black hole sitting at the center of one of these galaxies, pulling in surrounding gas and radiating enormous amounts of energy as that material heats up before falling in. Supermassive black holes are already known to exist far earlier in cosmic history than older models predicted comfortable, and an actively feeding black hole can genuinely outshine the combined light of every star in its host galaxy. If even a fraction of these ultra-bright early galaxies are being powered this way rather than by starlight alone, it would mean black holes started growing to significant size almost immediately after the first stars appeared, which is its own separate and very active area of debate. It's worth pausing here to be clear about what this discovery does not mean, because headlines love to overstate this kind of thing. This is not evidence against the Big Bang. The overall framework of an expanding universe cooling from an extremely hot, dense early state remains supported by an enormous and very well-tested body of independent evidence, from the cosmic microwave background radiation to the observed abundances of light elements to the large-scale structure of galaxies we see today. What is actually happening here is something narrower and, honestly, more interesting. The specific details of how quickly complex structure assembled inside that expanding universe are being revised because the observational evidence keeps pushing earlier and earlier than the models predicted. Science, running into a wall of inconvenient data and adjusting its models accordingly, is not science failing. It is science working exactly the way it is supposed to. And it's worth adding the honest caveats too, because a responsible account of this story includes them. Measuring the exact distance and properties of an object whose light has traveled across almost the entire history of the universe is an extraordinarily difficult technical challenge, and early results in any new frontier of astronomy do sometimes get revised once more data comes in. Sample sizes for these ultra-early confirmed galaxies are still small. Some early redshift estimates based only on imaging, without a confirming spectrum, have already been walked back after closer study. None of that erases the pattern that has emerged from properly confirmed, spectroscopically verified objects. But it does mean the picture is still actively being refined, not finalized. There's one more thread worth mentioning here, because it comes from a completely different corner of Webb's data, and it may or may not connect to everything we've just discussed. A separate group of researchers went through a large sample of spiral galaxies captured in Webb's deep field images and sorted them by the direction their spiral arms wind, essentially, which way each galaxy appears to be rotating from our point of view. In a universe with no built-in preferred direction, you would expect that split to land close to 50-50, roughly half spinning one way and half spinning the other. Instead, the count came back noticeably lopsided, with a clear majority rotating in the same direction. There is a fairly mundane possible explanation for this. Our own galaxy is moving through space, and that motion can subtly brighten objects rotating against our direction of travel, while dimming ones rotating along with it, which could introduce a real statistical bias into which galaxies get detected and correctly classified in the first place. If our current estimate of the Milky Way's own motion is even slightly off, that alone could account for the imbalance without requiring anything exotic. But some researchers have raised a far stranger possibility worth mentioning honestly. While being clear, it remains speculative and unproven. What if that imbalance is a faint leftover signature from the specific conditions our universe originally formed under, potentially connected to models in which our observable universe sits inside the interior of a black hole from some larger surrounding structure? It sounds like science fiction, and it may well turn out to be nothing more than a measurement bias once better data comes in. But it is a real hypothesis being seriously discussed in the scientific literature, not a talk show fringe idea, which says something about how open some of these foundational questions currently are. Step back and look at everything together, and here's the honest, balanced way to describe where we actually stand. We have galaxies from the dawn of cosmic time that appear too bright, too structured, and too chemically advanced for the models built to describe them. We have a possible rotational bias across large samples of galaxies that may be measurement error, or maybe hinting at something about the deep structure of the universe we don't yet understand. None of this is proof of anything final. All of it is a genuine, active, unresolved area of research being carried out by careful people using real data, not speculation dressed up as certainty. Roughly 13 billion years ago, in a universe barely a few 100 million years old, galaxies were already doing something they weren't supposed to be able to do yet. Their light has been crossing an expanding universe ever since, patiently waiting for someone to build a mirror large enough and cold enough and precise enough to finally catch it properly. We just did. And the very first thing that light told us, once we finally measured it correctly, is that we understand the early universe considerably less than most of us assumed a few short years ago. So here's the honest question worth sitting with. Is this the universe quietly telling us our models need a fairly modest update? Or is it the first crack in something much bigger that we haven't fully grasped yet? Nobody actually knows yet, and that's not a dodge. That's genuinely where the science currently stands. If you've got a theory of your own, drop it in the comments. I'd genuinely like to read it. And if this kind of deep, evidence-based look into space actually interests you, stick around and subscribe, because this is exactly the kind of story we dig into here. Real findings from real published research, explained clearly, without pretending we know more than we actually do.